Every detail in this story comes from real scientific research and observation. Something is moving toward you right now. It left the sun 8 minutes ago, traveling at 400 kilometers per second. It has no shape, no sound. You cannot see it coming, but when it arrives, when it collides with the top of Earth's atmosphere at an altitude of 100 kilometers, the sky tears open in green. There is a place on Earth where the darkness is total and the cold reaches 40 below zero, and the people there do not go inside. They tilt their heads back, they wait, because what happens above them cannot be explained with a single word, and it cannot be photographed in a way that captures what it feels like to stand beneath it. A curtain of light 60 miles wide moves like something breathing. It is not a reflection, it is not a projection. It is atoms, actual individual oxygen and nitrogen atoms, releasing photons of visible light after being struck by particles that traveled 93 million miles from the surface of the sun. You are about to go there. Tonight you are going to stand inside one of the most energetic events in the Earth's atmosphere, and by the time it is over, you will understand exactly what you were looking at. Not as a beautiful mystery, as a machine, one of the most elegant machines in the solar system. The color green, the color red, a faint, impossible violet along the upper edge. Each color is a signature. Each color is a specific atom at a specific altitude, releasing a specific amount of energy at the exact moment it was struck. Above your head right now, at 70 meters altitude, the air is faintly crackling with electricity you can almost hear. The same storm happening above the Arctic is happening simultaneously above Antarctica, a mirror display on the opposite end of the planet, connected to this one by field lines passing through the Earth's core. 1 billion tons of magnetized plasma left the sun 3 days ago. You have been waiting for it. At some point tonight, you will lie down in the snow. You will look straight up. The aurora will fill your entire field of vision, rays converging from every direction to a single point directly above your face. You will not move. You will not want to. The field beneath your back is 5,000 kilometers deep. The liquid iron core that generates the magnetic shield that makes this entire display possible. Without it, the solar wind would strip this planet bare. In 1859, the aurora was so bright it woke farmers from sleep. Telegraph operators sent messages with the machines unplugged. The sky above Cuba was green. Tonight will not be that extreme, but it will be enough. The sun threw something at us, the earth caught it, and the atmosphere sang. This is quiet science at bedtime. If this is your kind of story, a subscribe means everything right now. Just relax and feel free to let this play as you drift off to sleep. Now, imagine. The sun is not a quiet place. At its core, nuclear fusion converts 600 million tons of hydrogen into helium every single second. The energy produced at the core takes approximately 100,000 years to work its way outward through the radiative zone, bouncing, absorbing, re-emitting before it reaches the convective zone, where it finally begins to rise in massive columns of plasma toward the surface. By the time that energy reaches the photosphere, the visible surface of the sun, it has transformed into light, heat, and something else, something the early space age barely knew existed: the solar wind. The sun's outer atmosphere, called the corona, reaches temperatures of 1 to 3 million degrees Celsius, paradoxically far hotter than the surface itself, which sits at only about 5,500 degrees. At these extreme coronal temperatures, the sun's gravity is not strong enough to hold everything down. Particles, primarily protons and electrons, escape continuously in all directions, streaming outward at speeds between 300 and 800 kilometers per second. This is not a metaphor. This is a constant physical outflow of matter from the sun, traveling through space in every direction at once. The solar wind fills the entire solar system. It shapes the tails of comets, pointing them always away from the sun, regardless of which direction the comet is traveling. It compresses the magnetic fields of planets. It sculpts a vast bubble around the entire solar system called the heliosphere, which extends well beyond the orbit of Pluto and separates our solar environment from the interstellar medium beyond. Earth sits inside this wind constantly. You are sitting inside it right now, at this moment, as you listen to this. The solar wind is passing through the space above your head. It is interacting with Earth's magnetic field at an altitude of approximately 65,000 kilometers on the sunward side, and stretching Earth's magnetic field into a long tail on the night side that extends for hundreds of thousands of kilometers into space. The reason you are not harmed by this is not because the solar wind is gentle. It is because Earth has a shield. The geomagnetic field, the magnetosphere, is generated deep inside the planet, in the outer core, where liquid iron and nickel circulate in patterns driven by Earth's rotation and the heat difference between the inner and outer core. This circulation of conducting fluid generates electric currents, and those currents produce a magnetic field that extends far into space in all directions. The magnetosphere acts as a deflector. When the solar wind reaches it, most of the particles are bent around the planet and continue past. The field compresses on the sunward side and elongates on the night side. The boundary where the solar wind first encounters the magnetic field, where the wind slows abruptly from supersonic to subsonic speed, is called the bow shock. Behind it is the magnetosheath, a region of turbulent, slowed solar wind particles. And inside that is the magnetopause, the actual outer boundary of Earth's magnetic domain. For most of the time, this shield holds, but not always perfectly. The solar wind carries with it a magnetic field, the interplanetary magnetic field, which is an extension of the sun's own magnetic field, stretched and dragged outward by the outflowing plasma. This interplanetary magnetic field has a direction, and that direction matters enormously. When the interplanetary magnetic field is oriented southward, opposite to Earth's northward pointing magnetic field at the subsolar point, something extraordinary happens. The two fields connect. Magnetic field lines from the sun link directly to magnetic field lines from Earth in a process called magnetic reconnection. In that moment, the shield develops a door. Solar wind particles pour through. They travel down field lines toward the polar regions, guided along invisible magnetic channels that converge at 2 points on Earth's surface, the geomagnetic poles. You are standing beneath one of those convergence points right now. The air above you looks empty. It looks cold and black and still, but at an altitude of between 100 and 300 kilometers, something is about to happen to the individual atoms of oxygen and nitrogen that make up the upper reaches of Earth's atmosphere. Something is falling toward them at 400 kilometers per second. The incoming particles, electrons primarily, guided by the magnetic field, do not arrive gently. They slam into atmospheric atoms with enough energy to knock electrons out of their orbits entirely. The atoms are ionized. They are stripped of their electrons and left in an excited state, vibrating with absorbed energy they cannot hold. And then they release it. Each atom releases that energy as a photon, a single particle of light, at a wavelength determined by the atom's structure and the altitude at which the collision occurred. Atomic oxygen at altitudes between 100 and 150 kilometers emits the most commonly seen color, a yellow-green light at a wavelength of 557.7 nanometers. This is the green you see in almost every photograph of the aurora. It is the most efficient emission in this part of the atmosphere, and it is the signature of an oxygen atom returning to its ground state after being struck. Higher up, between 200 and 300 kilometers, atomic oxygen emits a deep red at 630 nanometers, a rarer, dimmer color that requires more energy to produce and is often only visible in strong auroral displays or in long exposure photographs. The lowest edge of the aurora, where the rays terminate and the atmosphere becomes dense enough to stop the incoming electrons entirely, glows with a faint blue-violet that is the hardest color to see with the naked eye. This lowest fringe exists at the exact altitude where the aurora ends and the stratosphere begins. Below it, nothing glows. The particles cannot reach any deeper. Each color is a measurement. Each color is altitude made visible. The aurora is a spectrum analyzer painted across the sky. You are standing in a field somewhere north of the Arctic Circle. The temperature is below -25 degrees Celsius. The ground beneath your feet is frozen solid to a depth of several meters, permafrost, ancient and undisturbed. The trees around you, black spruce and birch, are dusted in crystalline frost. There is no wind tonight. The air is so still and so cold that it feels solid. Above you, the Milky Way is fully visible, a pale river of light crossing the sky from horizon to horizon, hundreds of billions of stars reduced by distance to a smear of white against the black. And then, low on the northern horizon, something appears. It begins as a pale arc, a faint brightening of the sky, like the memory of a sunset in the wrong direction. You might mistake it for the glow of a distant city, but there are no cities in that direction. There is nothing in that direction for 1,000 kilometers. The arc brightens. It lifts slightly off the horizon, and then it begins to move. You are watching charged particles arrive. The arc develops structure. What was a smooth curve begins to show texture, vertical rays, like a curtain with fine folds hanging from the top of the atmosphere. These rays are not random. They are aligned with Earth's magnetic field lines, which angle downward toward the pole at this latitude. The particles follow those lines, and the light follows the particles, and the result is a geometry that looks intentional, architectural. The curtain brightens from yellow-green to a sharper, more saturated green. The folds deepen and tighten. The entire structure begins to undulate, a slow, rhythmic movement traveling from east to west along the arc, like a flag in a slow wind. This movement, this breathing quality, is not optical illusion. It is real. It is caused by variations in the density and energy of the incoming particle stream, which itself reflects turbulence and structure in the magnetosphere overhead. Waves travel along magnetic field lines. The aurora pulses in response. You are watching the magnetosphere move. Standing here in the cold, watching the sky shift and breathe, you are looking at an object that extends 65,000 kilometers above your head. The curtain you see, the bottom edge glowing green, the upper edge fading to red, where oxygen atoms at higher altitudes emit their weaker light. That curtain is the visible lower boundary of a process that fills an enormous volume of near-Earth space. The auroral oval, the ring-shaped zone where aurora most commonly appears, centered on the geomagnetic pole, typically sits at a geomagnetic latitude of about 65 to 72 degrees. From the ground, it looks like a display occurring just overhead. From space, it looks like a glowing ring encircling the pole, a permanent feature of Earth's magnetic environment, brightening and expanding during periods of high solar activity and retreating toward the pole when the sun is quiet. Satellites looking down at Earth from above the poles can photograph the entire oval at once, a complete ring of light, the full circuit of the auroral zone, glowing simultaneously across thousands of kilometers of latitude. From the ground, you see only a piece of it. But what a piece! The rays above you are now 30 to 40 kilometers wide and hundreds of kilometers tall, stretching from the lower ionosphere up toward the edge of space. The folds in the curtain tighten and accelerate. The movement shifts from a slow wave to something faster, a ripple, then a shimmer, and then it explodes. This is what Aurora scientists call a substorm onset. The magnetotail, the elongated night-side extension of Earth's magnetic field, has become overloaded with energy stored from the reconnecting magnetic field lines. The tail snaps. A new reconnection event occurs on the night side, releasing that stored energy in a rapid, explosive reconfiguration of the magnetosphere. The energy propagates inward toward Earth and downward along field lines toward the ionosphere. And the sky above you erupts. The arc overhead expands in seconds from a thin band to a broad canopy covering half the sky. The green intensifies until it is almost painful to look at directly. New rays appear and disappear in fractions of a second. Colors shift, green, then a deep red bleeding in from the upper edges, then a cold white blue at the lower fringe. The curtains fold and unfold in rapid succession. The entire display rotates, brightens, dims, and brightens again. It is, without question, the most dynamic light show produced naturally anywhere in Earth's environment. It lasts in its most intense form for 10 to 20 minutes. Then the substorm relaxes. The display settles back into a slower, steadier glow. The frantic movement gives way to the long, breathing rhythm that first drew your eye to the northern sky. You are still standing in the field. Your neck aches from looking up. Your feet are numb. You do not move. Above you, the atoms of the upper atmosphere continue to glow, each one a tiny machine converting kinetic energy into light, receiving particles from the sun and releasing photons back into the universe at wavelengths that cross the visible spectrum. The light above you is real. The process producing it has been running continuously for as long as Earth has had a magnetic field, for billions of years, long before there were eyes to see it, long before there was language to describe it. Tonight, you have eyes. Tonight, you are here. The cold settles in around you like something patient. The green curtain above shifts slowly, its lower edge sharp and luminous, its upper edge dissolving into the darkness of the sky beyond. Stars appear between the moving folds. The Milky Way, undimmed by any light pollution, runs from horizon to horizon. You are standing at the edge of something enormous, and the enormous thing is bending down to meet you. The display above you has settled into something steadier now. The frantic brightness of the substorm has passed, and what remains is a wide, slow band of green light moving across the sky from east to west in a long, rolling wave. The temperature has dropped further. Your breath rises in short clouds and disappears. You have been standing here for nearly an hour, and in that time the aurora has changed character 4 times. This is not unusual. The aurora is not a single static event. It is a continuous response, a real-time display driven by conditions 93 million miles away, mediated by a magnetic shield 65,000 kilometers overhead, and ultimately expressed in the individual collisions between particles and atoms in a layer of air 100 kilometers above your head. To understand why the aurora behaves the way it does, why it pulses, why it moves, why some nights it fills the entire sky from horizon to horizon, and other nights it appears only as a faint arc low on the horizon, you need to understand the sun more completely, not just as a source of light and warmth, but as a dynamic, variable star with its own weather. The sun rotates, not as a solid body. It is composed entirely of plasma, but differentially. The equatorial regions rotate approximately once every 25 days, while the polar regions complete a rotation in about 35 days. This differential rotation drags and twists the magnetic field lines embedded in the solar plasma, slowly winding them up like rubber bands over weeks and months. The sun also follows a cycle of magnetic activity with a period of approximately 11 years. During solar minimum, the magnetic field is relatively organized, with a clear north and south magnetic pole. During solar maximum, the field becomes disordered and complex, full of active regions where tangled magnetic field lines store enormous amounts of energy close to the surface. We are currently in solar cycle 25, and it has proven to be one of the most active cycles in recent memory, more energetic than scientists initially predicted. The sun has been producing more frequent and more powerful events, and Earth's aurora has been responding accordingly. The aurora is not just beautiful, it is a weather report. There are 2 primary types of solar events that intensify the aurora beyond its quiet background state. The first is the coronal mass ejection. The second is the solar flare. A coronal mass ejection, a CME, is an eruption from the sun's corona in which a massive bubble of magnetized plasma is launched into space. A typical CME contains between 1 billion and 10 billion tons of solar material. It travels at speeds ranging from a few hundred to several thousand kilometers per second. The largest, fastest CMEs can reach Earth in as little as 14 to 17 hours. The slower ones take 2 to 3 days. When a CME is directed toward Earth, it arrives at the magnetosphere carrying its own magnetic field. If that field is oriented southward, anti-parallel to Earth's geomagnetic field, the reconnection process is far more efficient. More solar wind energy enters the magnetosphere. The auroral oval expands to lower latitudes. The aurora that normally glows only above the Arctic Circle can appear over Scotland, Canada, the northern United States, and sometimes as far south as Texas or the Mediterranean. This expansion is measured using a geomagnetic index called the KP index, which runs from 0 to 9. A KP of 0 or 1 represents a very quiet magnetosphere. A KP of 5 indicates a geomagnetic storm, the threshold at which aurora becomes visible at mid-latitudes. A KP of 9, the maximum, represents an extreme geomagnetic storm, the kind that occurs only a handful of times per solar cycle. During a KP9 event, the auroral oval can expand to geomagnetic latitudes as low as 40 degrees, placing aurora potentially visible over cities like New York, Madrid, and Beijing. The most famous such event in the historical record is the Carrington event of 1859. On September 1st and 2nd of that year, the largest geomagnetic storm ever recorded struck Earth following a series of massive solar flares and a fast CME. Telegraph systems across Europe and North America failed, with operators reporting that they could send and receive messages even with the power disconnected. The induced currents from the geomagnetic storm were that strong. Aurora was visible as far south as Cuba and Hawaii. People in the northeastern United States reported being able to read newspapers by the light of the aurora at midnight. The Carrington event lasted approximately 2 days. Standing in your field in the Arctic, you imagine what that night must have looked like, not just here, but everywhere. Farmers in Ohio waking at midnight because the sky was too bright to sleep. Sailors at sea far from shore, watching the horizon turn green and red with no idea what they were witnessing. The sky above the entire northern hemisphere transformed into a continuous display of light. The aurora in that event was not a phenomenon of the far north. It was a planetary event. The sky above you pulses once, slowly, as if agreeing. The second major solar driver of aurora is the solar flare itself. Flares are bursts of electromagnetic radiation, primarily X-rays and extreme ultraviolet light, released when magnetic energy stored in active regions near sunspots is suddenly and violently converted into heat and radiation. A large X-class flare releases energy equivalent to billions of nuclear bombs in a matter of minutes. The radiation from a solar flare travels at the speed of light and reaches Earth in approximately 8 minutes, the same 8 minutes it takes sunlight to make the journey. When this radiation arrives, it ionizes the sunlit side of Earth's upper atmosphere, which can disrupt radio communications and GPS signals. This effect, called a radio blackout, is immediate and affects the day side of Earth. But flares also accelerate particles. The most energetic solar proton events can follow a large flare, sending high-energy protons racing toward Earth in hours. When these particles arrive and are funneled by the magnetic field toward the poles, they produce a different kind of aurora, a polar cap absorption event, visible only in the very highest latitudes and distinguishable from regular aurora by its more diffuse, less structured appearance. The green curtain above you tonight is not from a flare. Tonight's display is driven by a moderate coronal mass ejection that left the sun 3 days ago, a magnetic cloud of solar plasma that arrived at Earth's magnetosphere approximately 6 hours before you came outside. The KP index this evening reached 6, a moderate geomagnetic storm, enough to push the auroral oval 2 to 3 degrees of latitude equatorward, enough to guarantee a display across the entire subarctic band. You know this because of a network of instruments spread across the globe, monitoring the sun and the magnetosphere in real time. Spacecraft at the L1 Lagrange point, the gravitational balance point between Earth and the sun, about 1.5 million kilometers upstream, continuously measure the solar wind. When a CME passes the L1 point, scientists know it will reach Earth within 30 to 60 minutes, and warnings are issued. The spacecraft currently watching the solar wind from L1 includes instruments capable of measuring the magnetic field direction of the incoming solar wind to within fractions of a degree. It is that measurement, specifically whether the interplanetary magnetic field is pointing southward, that determines whether the night sky will be dark or alive with color. You had checked that measurement before you drove out here. The field was southward. It had been southward for 4 hours. The aurora was coming. You were right. The ability to check that measurement, to know hours before you drove out here that tonight would be worth the cold, is a product of infrastructure built over the last 6 decades specifically to monitor the space between Earth and the Sun. Space weather forecasting began as a practical necessity rather than a scientific curiosity. In 1989, a geomagnetic storm caused by a powerful CME knocked out power across the entire province of Quebec. Within 90 seconds, 6 million people lost electricity. The outage lasted 9 hours. Transformers were damaged across the northeastern United States. Aurora was visible as far south as Texas and Florida. The economic damage ran into hundreds of millions of dollars. That event made clear that modern infrastructure, power grids, satellites, pipelines, communication systems, is genuinely vulnerable to solar activity in ways that had been largely theoretical until that night. The response was a gradual but significant investment in space weather monitoring. Today, the Space Weather Prediction Center in Boulder, Colorado, operates continuously, 24 hours a day, every day of the year, issuing forecasts and alerts for geomagnetic storms, solar flares, and solar energetic particle events. Its forecasters use data from a network of satellites, ground-based magnetometers, and solar observatories to predict conditions up to 3 days in advance. The primary upstream sentinel is the Deep Space Climate Observatory, DSKOVR, positioned at the L1 Lagrange point between Earth and the Sun. DSKOVR carries instruments that measure the solar wind's speed, density, temperature, and magnetic field direction in real time, providing approximately 15 to 60 minutes of warning before the measured conditions arrive at Earth's magnetosphere. 15 minutes is not much time for a power grid operator to take protective action, but it is enough for automated systems to adjust transformer loads and for satellite operators to switch to safe modes. Alongside DSKOVR, the Advanced Composition Explorer, ACE, has been monitoring the solar wind from L1 since 1997, providing nearly 3 decades of continuous measurements that have become the baseline dataset for understanding how solar wind conditions translate into geomagnetic activity at Earth. Further back, closer to the Sun, the Solar and Heliospheric Observatory, SOHO, and the Stereo spacecraft watch the solar corona for emerging CMEs, allowing forecasters to identify ejections and estimate their direction and velocity up to 3 days before they might reach Earth. The forecast that brought you out here tonight came from this system. A CME was identified leaving the Sun's corona. Its trajectory was calculated. Its speed was estimated. Its magnetic field direction, the crucial southward component that would allow reconnection, was predicted with moderate confidence. A storm watch was issued. The watch was upgraded to a warning when DSKOVR measurements confirmed the southward field at L1. You checked the NOAA app on your phone, saw the KP forecast, checked the clear sky conditions, and drove north. The science that produced tonight's display is 300 years old. The science that let you know it was coming is 60. Both are standing here with you in the cold. The display above you is now expanding again, not explosively as it did during the substorm, but gradually, like a tide coming in. The arc that began on the northern horizon has moved directly overhead. The green is brighter now. You can see structure within the curtain that was not visible before. Fine, vertical striations, each one a bundle of magnetic field lines, carrying a slightly different density of incoming electrons. The rays brighten and dim individually, independent of one another. Some flare up and disappear in seconds, others remain steady for minutes. You are watching turbulence in the magnetosphere, made visible, eddies and waves in a system that occupies a volume of space larger than the sun itself. At the very top of the tallest rays, where they fade into the darkness above, there is a faint blush of red. You have to look directly at it to make yourself believe it is real. It is real. Atomic oxygen at 250 kilometers altitude, emitting its long wavelength 630 nanometer photon, the high altitude signature, visible only when the incoming particles have enough energy to reach the rarefied air above 200 kilometers. You hold that red color in your eyes for a moment. It is the color of the upper edge of the atmosphere. It is where the sky becomes space. Below the green, at the very bottom fringe of the most active rays, where they terminate in the lower ionosphere at around 90 to 100 kilometers, there is a dark purple-blue molecular nitrogen stripped of its electrons, releasing its own spectrum in the densest part of the Aurora zone. You have to look for it. It appears only where the rays are most intense, where the particle flux is high enough to reach this deeper altitude. Green above 90 kilometers, purple-blue below, red above 200. These colors are not decoration, they are a cross-section of the atmosphere, illuminated. You lower your gaze, the horizon to the east is still dark. The stars there are undisturbed. Orion is rising, a familiar pattern, visible from both poles to 30 degrees south latitude, the same stars that navigated every ocean before clocks were invented. To the west, the aurora has spread. What began as a northern phenomenon now fills the sky from northwest to northeast, a vast arc that if you could see it from space would appear as a curved band following the auroral oval, stretching across 5 time zones simultaneously. In Svalbard, at 78 degrees north latitude, researchers at the Kjell Henriksen Observatory are watching the same aurora you are watching, measuring it with all sky cameras, magnetometers, and ionospheric radars. In Tromsø, Norway, a small city built at the center of the auroral zone, tourists are lying on thermal blankets in the snow, watching the same green light. In Fairbanks, Alaska, on the other side of the planet, it is evening rather than midnight, and the display has just begun there too. The auroral oval wrapping continuously around the geomagnetic pole, active everywhere at once. This is a planetary event occurring right now, and you are standing inside it. The cold is becoming something familiar now. You have stopped noticing it. Your eyes have fully dark adapted. After 45 minutes in complete darkness, your retinas are operating at maximum sensitivity. The rod cells, the photoreceptors responsible for low-light vision, densest at the edges of the retina, have depleted their rhodopsin during the first 20 minutes of darkness and rebuilt it in the following 25. Now you are seeing with the most sensitive version of your own visual system. This is why the aurora looks better the longer you stand here. This is why experienced aurora watchers say the first 10 minutes are never the best 10 minutes. Your eyes are now capable of detecting light at intensities as low as a single photon per second per rod cell. The aurora is producing far more than that. A green aurora of moderate brightness generates roughly 100 to 200 Rayleigh of intensity, a unit used specifically for measuring diffuse atmospheric light. For comparison, the night sky background, the faint glow of starlight scattered by the atmosphere, is approximately 25 Rayleigh. The aurora, even at this moderate level, is roughly 5 to 8 times brighter than the ambient sky. Above you, in the most active portion of the display, the brightness is considerably higher. During the substorm peak an hour ago, the most luminous parts of the aurora may have reached several thousand Rayleigh, bright enough to cast faint shadows on the snow. You look down at the ground. The white of the snowfield has a faint green tint, not imagined, real. The aurora is bright enough to color the snow. You breathe slowly, in, out. The cold air fills your lungs and clears everything else away. There is nothing in your mind except what is above you. The green light continues its long, slow rhythm. The curtain folds and unfolds. A new ray appears directly overhead, intensely bright, and then dims over the course of 30 seconds, leaving only a faint afterglow in your vision that takes another 30 seconds to fade. The sky above you is in communication with the sun. Not metaphorically, physically. The solar wind is arriving continuously. The magnetosphere is processing it continuously. The aurora is the output, the light emitted by an atmosphere absorbing energy from 93 million miles away, converting that energy into photons and releasing them in every direction, including downward toward you, where they land in the photoreceptors of your dark-adapted eyes and become something you will remember for the rest of your life. And still the night is not finished. The KP index, according to the last reading you checked before you came outside, was still rising. The CME's leading edge has passed, but the full magnetic structure of the cloud is still arriving. The most intense part of the event, the region where the magnetic field rotates most strongly southward, is expected to arrive sometime in the next 2 to 4 hours. The aurora above you is not at its peak. What you have seen so far is the beginning. You settle your weight evenly between both feet. You tilt your head back. The cold sky presses down against your face, clean and absolute. The curtain above you ripples once, slowly from west to east, a single long wave traveling the full width of the display in approximately 8 seconds. You follow it with your eyes until it disappears off the eastern horizon. Then you look back to the north and wait for the next one. The hours before midnight in the Arctic in winter carry a particular quality of silence. There is no birdsong, no insects, no running water, every stream and river locked under ice. The only sounds are the occasional soft crack of a tree contracting in the cold, and the faint sound of your own breathing. The stars above are motionless. The aurora moves. You have been outside for 2 hours now. Your fingers, even inside thick gloves, are beginning to feel the cold in a deeper way, a pressure rather than a sting. But the display overhead has been building steadily for the last 30 minutes, and what you are watching now is not the same aurora that greeted you when you first arrived. The KP index has climbed to 7. The auroral oval has expanded southward by nearly 5 degrees of geomagnetic latitude since the evening began. Aurora that was visible only above 65 degrees north is now active as far south as 55 degrees, covering all of Scandinavia, Iceland, most of Canada, and Alaska. In cities that rarely see the aurora, people are photographing it from their backyards, but most of those displays are a faint shimmer low on the horizon, a soft green blush above the rooftops, a curiosity, not an experience. Here at the center of the oval, the aurora fills the sky. Above you, the display has taken on a new structure. Instead of a single arc or curtain, there are now multiple overlapping bands, 3, possibly 4 distinct structures stacked vertically in the sky, each at a slightly different altitude, and each with its own rhythm of motion. They move independently of each other. Sometimes they align, brightening in synchrony. Sometimes they oppose each other, one brightening as another dims. The overall effect is of depth, not a flat painting on the ceiling of the sky, but layers, like looking through multiple transparent sheets of varying luminosity. This is called an auroral corona, when multiple structures converge overhead and you look directly up. The perspective collapses the parallel rays into something that radiates outward from a single point directly above you, like the spokes of a wheel vanishing into the zenith. You tilt your head straight back and look at it. The rays extend from directly above you in every direction simultaneously, forming a dome of light with you at the center. At the outer edges, where the rays meet the horizon, they are nearly horizontal, traveling along lines of sight that cut through many times the thickness of the atmosphere, producing the broadest, most diffuse glow. Directly above, the rays are vertical, and the light is most intense, most sharply structured. You are standing at the focal point of the aurora. It feels in a way that is difficult to describe without sounding excessive, like standing inside a cathedral. The geometry has that quality, something reaching upward with intention, converging toward a single high point, filling the space below with light that moves. The science of why the corona forms directly overhead at the magnetic zenith, the point in the sky where the magnetic field lines point straight down into the Earth, is connected to the geometry of particle entry. Electrons following magnetic field lines arrive most densely at the magnetic zenith because that is where the field lines are oriented directly toward the observer's position on the ground. You are standing at the base of a magnetic funnel, and the aurora pouring down that funnel is concentrated into the smallest apparent angle. You are, in the most literal sense, inside the beam. Something is looking directly at you from 93 million miles away. Not metaphor, the sun's plasma, guided by magnetic geometry, has arrived at this precise point above your head. The atmosphere here, right here, at this latitude, at this longitude, on this night, is receiving a higher flux of incoming particles than almost anywhere else on Earth's surface. You are at the bottom of a river of charged particles flowing from the sun, and the river is lighting up the air above you. The color green is everywhere now. It fills your peripheral vision. It is bright enough that you can see your own shadow on the snow, faint but real, a shadow cast by the aurora, cast by particles that left the surface of the sun 3 days ago. Think about what that means. 3 days ago, a region of the sun's corona became unstable. The magnetic field lines threading through an active region had been twisted and stressed for days by the differential rotation of the solar surface beneath them. The energy stored in those tangled field lines, energy that had been building since the field structure first emerged from the solar interior weeks earlier, finally exceeded the force holding the structure together. In approximately 4 minutes, the equivalent of roughly 10,000 nuclear warheads worth of energy was released. 1 billion tons of magnetized plasma was launched from the sun at approximately 900 kilometers per second. The leading edge of the CME accelerated particles ahead of it to nearly the speed of light. These arrived at Earth within hours and were detected by radiation monitors on satellites and at polar research stations. The main body of the CME, the magnetic cloud, traveled for 3 days before reaching Earth. At the L1 monitoring point, instruments recorded the arrival, a sudden compression of the solar wind, a rotation of the magnetic field, a jump in particle density and velocity. The alert was issued. Geomagnetic Storm Watch upgraded to warning, predicted KP 7 to 8. And you drove out into the wilderness with a sleeping bag and a thermos of tea and waited. Now here you are, standing in the evidence. The causal chain from a magnetic instability on the surface of a star 93 million miles away terminates here in your retinas as green light. That chain is real. Every link in it is measurable. Every step has been observed and documented by scientists, using instruments ranging from solar observatories in geosynchronous orbit to ground-based magnetometers buried in the permafrost beneath your feet. The snow around you reflects the green light upward. It is not brilliant, nothing like sunlight, but it is present and real. The trees at the edge of the clearing cast faint shadows toward the south, away from the overhead glow. The shadows are green. You look down at your hands. The green light is on them too. Somewhere above the auroral display, at an altitude of several hundred kilometers, the zone of activity extends upward into the magnetosphere proper. The highest aurora ever recorded was observed at an altitude of nearly 1,000 kilometers. Rare, driven by extreme solar events, but real. Above that, the magnetic field lines stretch upward for tens of thousands of kilometers before curving back toward the sun or extending into the magnetotail. The aurora you see is the bottom kilometer, the narrow zone where the atmosphere is just dense enough to collide with the incoming particles, just rarefied enough to allow those particles to penetrate before stopping. Below about 80 kilometers, the atmosphere is too dense. The particles stop before reaching it. Above 300 kilometers, the atmosphere is too thin. Particles pass through without enough collisions to produce visible light. The aurora lives in a window, a specific, precise altitude range defined by the balance between particle energy and atmospheric density. That window is 100 to 300 kilometers, and from the ground, it is directly above you. You are looking at the ceiling of that window right now. The curtains above begin a new sequence of motion. The slower, breathing rhythm gives way to something more rapid, the beginning of another substorm. You recognize it now. The display brightens. The lower edge of the curtain, which had been sitting at around 10 degrees above the northern horizon, suddenly lifts. It accelerates upward across the sky and passes directly overhead in less than 20 seconds. The sky is now split. South of the zenith, the darkness is complete. Stars, Milky Way, the ordinary night sky. North of the zenith, the aurora fills everything. It is as if the sky has been divided by an invisible line, half dark, half light, the boundary running directly through the point where you are standing. And then the bright half brightens further. The green deepens. A new color begins to emerge along the upper portion of the display. A crimson red, stronger than the faint blush you saw earlier, now genuinely visible to the naked eye. It runs along the top of the tallest rays in long, horizontal streaks. Not the structure of the green below, but something more diffuse, more atmospheric, like the last light of a sunset that has no sun. This red is not the same emission as the green. The green is the allowed transition of atomic oxygen, a fast, efficient emission that produces most of the aurora's light. The red at high altitude is what physicists call a forbidden transition. In the dense lower atmosphere, an excited oxygen atom would collide with another atom before it had a chance to emit this particular photon, and the energy would be transferred away without light. But at 200 to 300 kilometers, the atmosphere is so thin, a near vacuum by terrestrial standards, that the atom can remain in its excited state for up to 110 seconds before emitting. At these altitudes, there is enough time. The forbidden transition becomes allowed. Red aurora at high altitude is oxygen buying itself enough solitude to finally let go of what it was holding. You watch the red spread. It moves more slowly than the green below it. It is not driven by the same fast dynamics of the lower ionosphere, but reflects conditions in the higher atmosphere where the physics operates on longer timescales. The red persists even as the green below it brightens and dims and brightens again. The two layers of color exist simultaneously. They are not at the same altitude. They are not produced by the same physical process. They are not even produced by the same type of oxygen. One is atomic, one involves different electronic transitions. But from the ground, they appear to occupy the same volume of sky, stacked vertically, green below and red above, the entire structure moving as one. To your right, on the eastern side of the display, a new formation is developing. A series of rapidly flickering patches, small oval areas of aurora, pulsing on and off with a period of roughly 2 to 10 seconds. This is pulsating aurora, a distinct phenomenon from the structured curtains and rays of the main display, caused by waves in the magnetosphere that modulate the precipitation of electrons in a rhythmic pattern. The pulses are not random. They have a frequency. They repeat. The mechanism is a wave called an electromagnetic ion cyclotron wave, generated in the equatorial magnetosphere and propagating along field lines toward Earth. These waves interact with electrons, periodically accelerating and scattering them toward the atmosphere in packets. The result, on the ground, is a pattern of light that blinks on and off like a slow strobe across the eastern sky. Three phenomena are now active simultaneously: the main curtain structure overhead, the high-altitude red diffuse glow above it, and the pulsating patches to the east. You are watching the magnetosphere operate on 3 different timescales and 3 different physical mechanisms at once. The display is extraordinarily busy, and yet, perhaps because of the cold, or the dark, or the hours of standing still, you feel no urgency to catalog or explain what you are seeing. You are simply watching. The explanations are there when you want them. The science sits underneath everything like bedrock, but right now you are watching light move in ways that light does not usually move, and you are letting it do that without trying to hold it. The pulsating patches to the east dim and stop. A minute passes, then they begin again at a slightly higher frequency. The magnetosphere has adjusted, the wave has shifted. You let your eyes move across the entire sky, from the structured green curtains overhead to the red diffuse glow above them, to the now quiet eastern patches, to the southern horizon where the sky remains completely dark and the stars are motionless. The temperature gauge on your pack reads -29 Celsius. You have been outside for 2 hours and 20 minutes. You sit down on the snow, not from exhaustion, because standing has started to feel wrong for this. This is something you should be horizontal for. You lie back on the snowfield, arms at your sides, and look directly up. The entire sky is above you. Every part of it. The aurora fills your entire visual field. The stars are behind it. The Milky Way runs beneath it, ghost pale, half hidden. Directly above the magnetic zenith, the rays converge in that same radial pattern, the corona. But now that you are lying down, your perspective has shifted. The convergence point is directly above your face. The rays extend outward from it toward every horizon equally. You are at the center of a sphere of light. The atoms above you have been waiting for this for billions of years. Not waiting with intention, waiting as a consequence of physics. The atmosphere has always been here. The magnetic field has always been here. The sun has always been streaming particles toward every planet in the solar system. And every time those particles arrived at Earth, the same collisions happened, the same photons were released, the same colors appeared. Long before humans walked this latitude, long before anything breathed on this planet, the aurora appeared. Night after night in an empty sky, in a world of ice and rock and cold water, the same green light moved through the same altitude band, above the same geomagnetic pole. No one was there to see it. The atoms did not know. The photons were released and traveled in all directions and struck nothing but snow. And then, one geological moment ago, there were eyes. You close yours. The cold is deep now, past discomfort, past sensation, past thought. You are aware of the weight of your own body against the frozen ground. You are aware of the silence. You are aware in some diffuse way that does not require language of the enormous processes occurring above you. Particles arriving, atoms colliding, light being born and dying in 100 millionth of a second, over and over, in a continuous rain of photons falling on the dark side of a rotating planet. The earth beneath your back has not moved in any measurable sense since you lay down on it. The sky above has not been still for a single moment. You are the still point, the fixed object around which everything else is moving, the aurora, the magnetosphere, the solar wind, the sun itself, rotating on its axis, churning its magnetic field, releasing its plasma into the heliosphere in all directions. You are still. Everything is moving. And the cold holds you in place against the ground as gently as gravity holds the moon. Beneath your back, 5,000 kilometers straight down, lies the source of the magnetic field that made tonight possible. Earth's outer core is a sphere of liquid iron and nickel, approximately 2,300 kilometers thick, surrounding a solid inner core, roughly the size of the moon. The outer core is in constant motion, large-scale convective flows, driven by heat escaping from the inner core, and by the Coriolis effect of Earth's rotation. These flows move slowly by human standards, but carry conducting liquid metal across enormous distances, and moving conducting fluid generates electric currents, and electric currents generate magnetic fields. This is the geodynamo, the self-sustaining engine at the center of the Earth that has been maintaining the planet's magnetic field for at least 3.5 billion years. The geodynamo is not static. The field it produces shifts over time. The North Magnetic Pole, currently located in the Canadian Arctic, has been drifting towards Siberia at approximately 55 kilometers per year. a rate that has been accelerating since the early 2000s. It has moved approximately 2,000 kilometers over the last century. Over geological timescales, the field does something more dramatic. It reverses. The magnetic North Pole becomes the magnetic South Pole, and vice versa. These reversals occur at irregular intervals, averaging every 200,000 to 300,000 years. The last reversal, the Brunhes-Matuyama reversal, occurred approximately 780,000 years ago. During a reversal, the field does not flip instantaneously. It weakens first. It becomes chaotic, multipolar, potentially hosting several north and south poles simultaneously for thousands of years before gradually reorganizing into its reversed configuration. During this transition, the magnetosphere's shielding capacity is significantly reduced. What happens to the aurora during a geomagnetic reversal is still being studied through paleomagnetic records, fossil magnetic signatures in ancient volcanic rock that preserve the field's direction at the moment of formation. What those records suggest is that the auroral oval during transitional periods does not form clean rings around the poles. It fragments, it wanders to unexpected latitudes, it becomes multiple overlapping zones of activity rather than a single coherent ring. The aurora of a reversing Earth would look nothing like what is above you tonight. The field above you is one of the quieter interludes in 4 billion years of restless magnetic history. Tonight, with the field intact and the oval sitting where it belongs, you are watching the aurora in one of its more stable configurations, the version that has persisted through most of human history, the version that confused compass needles for centuries before the magnetic poles were mapped, the version that the Inuit, the Sami, and the Norse looked up at and built into their understanding of the world. The geodynamo below your back is the reason any of this is possible. The aurora and the Earth's core are connected. The field that guides the particles down is the same field generated by the churning metal 5,000 kilometers beneath you. Fire above, fire below. You in the middle, lying on the snow. You open your eyes. The sky above you has changed again. The multiple layered structures have merged into a single, broad, diffuse band, not the sharp-edged curtain from earlier, not the explosive brightness of the substorm peak, but something wider and calmer, a slow breath taken by the magnetosphere after the exertion of the previous hours. The red at the top has faded. The pulsating patches to the east have gone quiet. What remains is the deep, steady green of oxygen at 100 to 150 kilometers, the backbone emission, the color that was here before you arrived and will be here after you leave. The KP index, if you could check it now, would show it settling back toward 5. The most intense phase of the geomagnetic storm has passed. The magnetic cloud at the heart of the CME has moved through Earth's magnetosphere. What is arriving now is the trailing edge, still enhanced solar wind, still some southward magnetic field component, but less organized and less powerful than the core of the cloud. The aurora is winding down, not disappearing. The auroral oval is still active. The display above you is still genuinely beautiful. Green light moving slowly across a sky full of stars, a structure easily 100 kilometers wide and several hundred kilometers tall, visible from space as a glowing band running from horizon to horizon. But the frantic energy of the substorm hours has given way to something more sustained and less dramatic. The slow burn. You stand back up. Your legs are stiff. You walk a short distance to keep the circulation moving, crunching through the snow crust, watching the aurora from different angles as you move. From the side, the curtain structure is clearer. You can see the vertical depth of it, the way the rays do not quite overlap, but are instead separated by thin, dark lanes, each lane a column of slightly less active precipitation. The aurora has texture in the horizontal dimension as well as the vertical. It is not a uniform sheet of light. It is a patterned structure, and the pattern reflects the patterning of the particle precipitation in the ionosphere above, which in turn reflects the structure of the magnetic field and wave activity in the magnetosphere above that. Every feature you can see has a cause. Every dark lane, every bright ray, every slowly moving wave, all of it is information. All of it is a readout of processes occurring in a region of space that extends from 100 kilometers above your head to 65,000 kilometers above your head, a volume of space more than 10 times the diameter of Earth itself. You are reading a system that is larger than the world. The history of humanity's understanding of the aurora is almost as interesting as the aurora itself. For most of human history, it was experienced without explanation, a light in the sky that moved, that appeared and disappeared without warning, that produced sounds some observers claimed to hear, but that others denied entirely. The Norse called it the Northern Lights, and attributed them to the shields of the Valkyries, reflecting light from Asgard. Finnish mythology described the aurora as a cosmic fox running across the sky, its tail brushing sparks from the mountaintops. The Menominee people of the Great Lakes described the aurora as the light of torches carried by great beings who used them to spearfish through the ice at night. These are not primitive misunderstandings. They are attempts to describe something genuinely mysterious, using the conceptual tools available. And in each case, the description captures something real about the experience. The movement, the light, the grandeur, the sense of something living occurring above. The scientific investigation of the aurora began in earnest in the 18th century. In 1741, the Swedish scientist Anders Celsius, who also gave his name to the temperature scale, observed that a compass needle deflected during periods of active aurora, suggesting a connection between the lights and Earth's magnetic field. This was the first measured quantitative link between the aurora and geomagnetism. Around the turn of the 20th century, Norwegian physicist Christian Birkeland proposed that the aurora was caused by electrons emitted from the sun being guided by Earth's magnetic field toward the poles. He built a model, a magnetized sphere in a vacuum chamber, and demonstrated that electron beams aimed at it would create patterns of glowing gas concentrated at the magnetic poles, similar in appearance to the aurora. His proposal was largely rejected by the scientific establishment of his time. The physicist Sidney Chapman argued that space was too good a vacuum to carry electric currents, and that the solar-terrestrial connection Birkeland proposed was physically impossible. Chapman was wrong. Birkeland was right. In 1958, Explorer 1, the first successful American satellite, discovered the Van Allen radiation belts, the first evidence that space near Earth was filled with energetic charged particles. In 1959, the Soviet Luna 1 spacecraft provided the first measurements of a continuous plasma flux flowing from the sun. By 1962, NASA's Mariner 2 confirmed that this outflow, the solar wind, was a permanent feature of interplanetary space, not a temporary phenomenon. By the early 1960s, The basic picture Birkeland had proposed 60 years earlier was confirmed. The sun continuously emits charged particles. Those particles interact with Earth's magnetic field, and the result at the poles is aurora. The field-aligned currents that carry energy from the magnetosphere down into the ionosphere are now called Birkeland currents. In his honor, spacecraft have measured them directly. They flow continuously in two great systems around each magnetic pole, one sheet of current flowing into the ionosphere, another flowing out, carrying hundreds of thousands of amperes of electrical current through near-Earth space. You are standing at the base of a current sheet carrying more electricity than any human-made power grid has ever generated. The atoms above you are the load at the end of that circuit. The aurora is what electricity looks like when the load is an entire atmosphere. Somewhere above you, the circuit is flowing right now. You look at the aurora differently now, not less beautiful, more so because beauty is more durable when it rests on understanding. The moving light above you is not an accident. It is not decoration. It is the visible expression of a planetary electrical system that has been operating continuously for as long as Earth has had a magnetic field, for approximately 4 billion years. The auroral oval has been glowing in one form or another since before the first living cell divided in the early ocean. There is a phenomenon that scientists discovered relatively recently, only in the 1990s, that extends the aurora story further than anyone previously suspected. Above the visible auroral display, extending to altitudes of 40 to 90 kilometers above the cloud tops, there exists a second family of atmospheric electrical events that are, in some ways, even stranger than the aurora below. These are called transient luminous events, and they were first captured on film by accident in 1989, when a researcher testing a low-light camera happened to point it at a thunderstorm and saw what appeared to be a column of red light shooting upward from the cloud tops toward the ionosphere. Sprates, as they are now called, are electrical discharges that propagate upward from thunderstorm anvil clouds to the lower ionosphere at altitudes of 40 to 90 kilometers. They occur in clusters, typically within a few milliseconds of powerful positive lightning strokes below. They are dim, typically visible only to very sensitive cameras or dark-adapted eyes under ideal conditions, and they last only 1 to 10 milliseconds. But they are real. They have been imaged from space, from aircraft, from high-altitude observatories, and by amateur sky watchers with sensitive cameras and a great deal of patience. Sprates are red at their tops and blue at their bottoms, again a color signature of atmospheric composition and altitude. The red is nitrogen at upper altitudes. The blue is nitrogen at lower altitudes. They extend from the lower edge of the ionosphere downward, and they sometimes show fine structure, tendrils, columns, jellyfish-like shapes that reflect the electromagnetic dynamics of the discharge. Above sprites, at even higher altitudes, there are elves, not the mythological kind, but a term that is an acronym for emissions of light and very low frequency perturbations due to electromagnetic pulse sources. Elves are expanding rings of light that appear at about 90 kilometers altitude, propagating outward from a point at the speed of light, lasting less than a millisecond. They are caused by the electromagnetic pulse from lightning reaching the ionosphere and inducing secondary emissions. Jets, blue jets, shoot upward from thunderstorm tops to altitudes of 40 to 50 kilometers in the middle stratosphere with velocities of tens of kilometers per second. The atmosphere is not quiet. It is full of electrical processes that span from the surface of the ground to the edge of space, many of them still being characterized, many of them only discovered in the last 3 decades. The Aurora is the largest and brightest of these electrical displays, but it shares the sky with a family of phenomena that together form a continuous electrical system linking the thunderstorms of the troposphere to the magnetosphere in near space. You are standing at the boundary between the calm and the charged. The world above you is not empty. A cloud drifts in from the west, not a thick cloud, thin, high cirrus, ice crystals at 12,000 meters altitude, the very top of the troposphere. As it moves across the lower quarter of the sky, it partially dims the aurora behind it, not blocking it, but softening it. The green takes on a milky quality through the cirrus, diffused slightly by the ice crystals. You watch the cloud pass. It takes 4 minutes. The stars reappear. The aurora behind it is unchanged. Ice crystals at 12 kilometers, aurora at 100 kilometers, both visible simultaneously, both made of entirely different substances, governed by entirely different physics, coexisting in the same line of sight. The atmosphere is layered. Most weather, clouds, precipitation, temperature variation, wind, occurs in the lowest 12 to 15 kilometers, the troposphere. Above that is the stratosphere, extending to 50 kilometers, where the ozone layer absorbs ultraviolet radiation. Above that, the mesosphere, extending to 85 kilometers, where the coldest temperatures in Earth's atmosphere occur, around -100 degrees Celsius. And above that, the thermosphere, where Aurora lives, where temperatures paradoxically rise again to hundreds or even thousands of degrees, heated by the absorption of solar ultraviolet and X-ray radiation, even as the gas is so thin it would feel like a hard vacuum to your skin. You exist at the bottom of all of this, at the densest, warmest, most protected layer, crushed toward the ground by an atmospheric column 12 kilometers high, kept warm by its blanket of greenhouse gases, sheltered from radiation by the ozone above and the magnetic field above that. You are at the bottom of a series of nested shells, each one protecting you from a different kind of energy coming from space. And tonight, the outermost shell, the magnetic one, is doing its job spectacularly. The energy that arrived from the sun 3 days ago has been intercepted, diverted, partially captured, and released as light. The most violent solar event in several months has been translated, by the time it reached you, into green light moving quietly across a silent sky. The shield is holding. Earth is not the only planet where this happens. Every planet in the solar system with a significant magnetic field produces aurora. Jupiter produces the most powerful aurora in the solar system, a continuous massive display that dwarfs anything possible on Earth. Jupiter's magnetic field is approximately 20,000 times stronger than Earth's, and its auroral ovals pump out power roughly 1,000 times greater than Earth's. The Jovian aurora is powered not only by the solar wind, but by Jupiter's own rapid rotation. The planet completes one rotation in just under 10 hours, and by volcanic activity on its moon Io, which injects enormous quantities of sulfur dioxide gas into the Jovian magnetosphere. The ionized sulfur and oxygen from Io's volcanoes are accelerated and funneled toward Jupiter's poles, creating an aurora with features that have no equivalent anywhere else in the solar system. Saturn produces aurora visible in ultraviolet light, driven by both solar wind and interactions with its moon Enceladus, which ejects water vapor from its subsurface ocean into Saturn's magnetosphere. Uranus and Neptune produce aurora as well, though their unusual axial tilts. Uranus rotates on its side, and Neptune's magnetic field is offset significantly from its rotation axis, mean that their auroral dynamics are more complex and less predictable than on Earth or Jupiter. Mars, which lost its global magnetic field approximately 4 billion years ago, still produces aurora, but of a fundamentally different kind. With no global dipole field, Martian aurora occurs above localized regions where ancient crustal magnetization still creates pockets of field strong enough to funnel solar wind particles. These patches of crustal magnetic field are the remnants of Mars's long-dead dynamo, preserved in the rock when the planet's core cooled and the global field died. The aurora that appears above them is patchy, irregular, and tied to geography rather than latitude. In 2023, the MAVEN spacecraft detected a global aurora on Mars following an intense solar event, ultraviolet aurora appearing across the entire night side of the planet simultaneously, produced not by magnetic guidance, but by direct bombardment of the atmosphere by energetic solar particles, with no magnetic shield to deflect them. This is what Earth's aurora would look like without the geomagnetic field. Not concentrated at the poles, not structured into ovals and curtains, but diffuse, global, appearing everywhere at once. Every time the solar wind is strong enough to reach the atmosphere directly. The beauty of Earth's aurora, the structure, the curtains, the rays, the ovals, the ordered geometry, is entirely a product of having a magnetic field. Without it, the light would still be there, but the architecture would be gone. What you are watching is what magnetism looks like when it catches light. You have been outside for nearly 3 hours. The cold has moved past pain and into something that feels almost like warmth. The body's final thermoregulation effort in extreme cold, sending more blood to the extremities in a last attempt to equalize temperature. You are not in danger. You are dressed properly, and you have shelter nearby, but you recognize the signal. It is time to begin thinking about going inside. Not yet. The aurora above has settled into a slow, meditative rhythm. The curtain is perhaps 60 degrees wide now, centered slightly east of north, moving in long, gentle waves that take 10 to 15 seconds to travel its full width. Each wave is the same brightness, the same green, the same smooth undulation from west to east along the arc. It is the most peaceful version of the aurora, not the most spectacular, but the most sustainable, the kind of display that asks nothing of you, the kind you can simply watch without needing to respond, the kind that lets you think about other things, or nothing at all. In Scandinavia, there is a tradition among people who spend their winters in the far north. When the aurora is active, you go outside, not to photograph it, not to explain it to guests, not to mark it as an item on a list, but simply to be present with it, to stand in its light, to acknowledge that something unusual and large and beautiful is happening above you while you are alive to see it. This tradition requires no particular understanding of magnetospheres or solar wind or Birkeland currents. It requires only the willingness to be cold for a while and look up. The science adds a dimension that the tradition alone does not provide, but the tradition provides something the science alone cannot: the willingness to simply stand in the light and not explain it, not capture it, not make it mean anything beyond what it already is, which is the sky tonight is full of green light. And you are here. The long wave in the Aurora completes its eastward run and disappears over the horizon. A pause, then another wave appears in the west and begins its slow journey. The night continues. The cold continues. The green light continues. You breathe slowly. The air fills your lungs with its particular flavor, dry, clean, cold enough to feel like drinking. Your exhaled breath rises and vanishes almost instantly in the still air, absorbed back into the cold before it can accumulate. Above you, at 100 kilometers, an oxygen atom absorbs the kinetic energy of an incoming electron and holds it for a fraction of a second before releasing it as a single green photon at 557.7 nanometers. That photon travels downward at the speed of light, covering 100 kilometers in 333 microseconds, and arrives at your retina. One photon from one atom at one altitude, driven by one electron from one star. There are 100 billion of them arriving every second. You see it all as green. The eastern sky is beginning to hold a suggestion of something that is not quite light and not quite dark, a distinction so slight that you cannot be certain whether you are seeing it or imagining it. It is not dawn. Dawn is still 3 hours away, but the sky at the horizon carries a quality that is different from the zenith, a depth that the hours of watching have made you sensitive to. The stars near the eastern horizon are as bright as they were at midnight. The difference is something else, a shift in the air, a change in the quality of the cold. The temperature has dropped another 2 degrees. It is now minus 31 Celsius. At this temperature, exhaled moisture freezes almost immediately. You can feel tiny crystals of ice forming at the edge of your scarf, where your breath meets the fabric. The snow around you has taken on a quality of absolute stillness, locked by cold into complete rigidity, every crystal and every flake as motionless as stone. The aurora overhead has continued its slow transition. What began the evening as a structured, dynamic display of curtains and rays has become something broader and more diffuse, a wide band of soft green light that extends from northwest to southeast across the zenith, its edges unsharp, blending into the sky around it rather than cutting cleanly against it. It moves, but the movement now is more like the shifting of a very slow current than the snapping of a curtain in wind. This is the late night aurora, the calm after the storm. The magnetosphere, after hours of elevated activity, is restoring its equilibrium. The CME's magnetic cloud has passed. The solar wind is returning toward its background state, still flowing as it always flows, but no longer carrying the enhanced field and density that drove the storm. The reconnection rate at the magnetopause is decreasing. The Birkeland currents are weakening. The flux of electrons arriving at the ionosphere is diminishing. The aurora is responding, slowly, not gone. It will be here for hours more, but quieter. There is a scientific term for what you are watching, the recovery phase of a geomagnetic storm. After the main phase, the period of intense activity when the D index, which measures the disturbance in the equatorial horizontal component of Earth's magnetic field, reaches its most negative value, the magnetosphere gradually returns to its quiet time configuration. Injected particles gradually drift out of the inner magnetosphere. The ring current, a torus of energetic particles encircling Earth at altitudes of 10,000 to 60,000 kilometers, slowly decays as those particles are lost to the atmosphere or scattered by wave-particle interactions. Recovery can take hours to days for the most intense storms. Tonight's storm will likely be fully recovered by tomorrow evening. The magnetosphere will return to its baseline state. The auroral oval will contract back to its quiet time position above 65 to 70 degrees geomagnetic latitude. The sky above cities in mid-latitudes will be dark again, and the process will begin again. The sun is still rotating. The active regions are still there. New ones are emerging. The 11-year solar cycle is continuing its progression toward maximum. The next CME could be days away, or weeks. The sun is not finished. It is never finished. You walk slowly across the snowfield to a slight rise at its edge, a low ridge of ground that gives you an unobstructed view in all directions. From here, on a clear night, the horizon is uninterrupted for approximately 40 kilometers in every direction. You can see the complete arc of the Aurora simultaneously, not just the overhead portion, but the full sweep of it from where it begins in the northwest to where it fades in the southeast. It is, seen all at once like this, genuinely vast. You are looking at a structure that spans, at this moment, approximately 3,000 kilometers of Earth's surface, from somewhere above the northern coast of Norway to somewhere above the central regions of Canada. If you could float above it and look down, the way the satellites do, you would see it as a continuous glowing ring around the geomagnetic pole, 3,000 kilometers in diameter, lit from within, turning slowly with Earth's rotation. Every point on that ring is producing the same green light, the same oxygen atoms, the same altitude, the same photon wavelength. 3,000 kilometers of identical physics occurring simultaneously, coordinated by a magnetic field that threads through all of it at once. The aurora is not local, it is continental. It is planetary. And yet here, at this latitude, at this moment, it feels entirely personal, as if the light above you is here because you are here, arranged for your particular viewing angle and your particular dark-adapted eyes and your particular tolerance for cold. You know this is not true. You know the aurora does not know you exist. The oxygen atoms do not register your presence. The electrons arrive regardless. The photons fall in every direction with complete indifference to what is below. And still, you feel found. That feeling is not embarrassing, and it is not irrational. It is the natural response of a nervous system that evolved in a world where being seen meant safety, where light meant warmth, where the sky mattered. The aurora triggers something very old in the part of the brain that monitors the environment for signals of significance. The signal this old part of your brain is receiving is something large is happening above you, and it is made of light. And you are responding the way your ancestors responded to fire, to sunrise, to any light that appeared in darkness, with attention, with stillness, with the specific quality of alertness that does not require action but simply witnesses. This is one of the oldest experiences available to a human being in the modern world, not because it is primitive, because it is unchanged. The aurora that appeared above the geomagnetic poles 100,000 years ago was the same aurora that is above you now. The same physics, the same colors, the same slow breathing rhythm. The people who stood beneath it then felt what you feel now. Not exactly in the language or the concepts, but in the body, yes. In the base of the throat, in the back of the eyes, in the quality of silence that falls when something very large is happening and you have no words for it. You have words for it now: geomagnetic storm, Birkeland current, magnetic reconnection, oxygen forbidden transition, interplanetary magnetic field southward turning. The words do not replace the feeling. They add to it. They give it depth. They let you know that what you are feeling is not fantasy. It is a response to something real and measurable and verified by instruments and confirmed by a century of increasingly sophisticated science. The feeling is real because the thing is real. And the thing is very real. There is one more thing about the aurora that science has only recently begun to confirm. For centuries, observers in Scandinavia, Finland, and Alaska reported hearing sounds during intense auroral displays. A faint crackling, a hiss, something like the rustling of fabric. These reports were dismissed for decades by scientists on physical grounds. The aurora occurs at 100 kilometers altitude, and at that altitude the atmosphere is so thin that sound waves cannot propagate. Any sound generated at 100 kilometers would dissipate long before reaching the ground. The observers were not wrong. In 2012, Finnish researcher Unta Lane published the results of years of careful acoustic monitoring during auroral activity. He identified sounds at ground level that correlated precisely with geomagnetic disturbances, occurring at altitudes of only about 70 meters above the surface, not at the aurora itself, but in a layer of air near the ground. His hypothesis: during geomagnetic storms, the boundary between differently charged layers of the lower atmosphere is disrupted, and the resulting electrostatic discharge produces faint crackling and hissing sounds at ground level. The aurora itself does not make sound, but the geomagnetic storm that produces the aurora can induce electrical effects at the surface that the human ear can detect. The sound of the aurora is real. It just comes from directly above your head, not 100 kilometers up. You listen. The field is still. The trees are still. There are no sounds from the natural world. No wind, no running water, nothing breathing. And then faintly you hear it. A soft crackling, like static at very low volume. Like the sound a wool blanket makes when you pull it in the dark. It lasts for a few seconds and stops. Then again, brief, irregular, not loud enough to be certain of, but present enough that you notice it every time. The geomagnetic storm expressing itself in your air. The aurora is speaking at the lowest possible volume. High above the auroral display, at an altitude of approximately 350 kilometers, the International Space Station is passing over the Arctic on one of its 16 daily orbits. The crew aboard, 6 people, sealed in pressurized modules, traveling at 7.7 kilometers per second, can look down and see the aurora from above. They do not see green from above. They see a thin, curved layer of luminosity hugging the upper boundary of the atmosphere, a dim ribbon of light visible against the black of space, curving with the planet below. From orbit, the aurora looks almost fragile, a thin atmospheric breath, a faint haze of light that would be invisible against the sun's glare on the day side. From orbit, the Earth's atmosphere, all of it, from the surface to the top of the thermosphere, is visible as a layer no thicker than the skin of an apple relative to the size of the planet. The aurora lives in that skin. You live at the bottom of that skin. The entire system that produced tonight's display, the solar wind, the magnetosphere, the ionosphere, the currents, The collisions, the photons, all of it is occurring within a shell so thin relative to the size of the Earth that from a few thousand kilometers up it is nearly invisible. From where you are standing, it is everything. The last deep cold of the early morning presses against you evenly from all sides. You are aware of the weight of your clothing. You are aware of the sound of your own heartbeat in your ears, which happens in very deep silence. You are aware, in the way you become aware of your breathing when someone points it out, of the rhythm of your own body, steady, slow, fully adapted to the cold and the dark and the hours of watching. The aurora above continues its long, diffuse drift. The green band moves westward now, not rapidly, but perceptibly. The Earth has been rotating beneath it for hours, and the display that was directly north when you arrived is now shifted slightly west of north, carried by the planet's rotation beneath the nearly fixed auroral oval. You are on a rotating planet. The aurora is pinned approximately to the geomagnetic pole. You and the aurora are in motion relative to each other. Everything is always in motion relative to everything else. The snow under your feet is moving at approximately 300 meters per second through space, carried by Earth's rotation. The Earth is moving at approximately 30 kilometers per second in its orbit around the Sun. The Sun is moving at approximately 220 kilometers per second around the center of the Milky Way galaxy. The galaxy itself is moving at approximately 600 kilometers per second relative to the cosmic microwave background radiation. You are not still. You have never been still. No part of the universe is still. But right now, in the reference frame of the frozen field and the silent trees and the green light, you're as close to still as anything gets. Breathe in, out. The air moves from the world into you and then back into the world. The molecules of nitrogen and oxygen that fill your lungs right now were, moments ago, in the open air above a frozen lake, several kilometers from where you are standing. They will be dispersed across the landscape by morning. The aurora above you is made of the same molecules. Not these specific ones. The ones above you are at 100 kilometers, while the ones you are breathing are at essentially 0. But they are the same elements. The same nitrogen and oxygen that produce the blue and green and red of the aurora are the same nitrogen and oxygen that sustain your life. The atmosphere above you is not separate from you. It is continuous with you. You are the bottom of the thing that is glowing. This is not a metaphor. This is molecular reality. You tilt your head back one more time and look directly up. The corona is gone now, the central convergence point that made the display feel like a dome, like a cathedral, like a beam aimed at you. The display has spread and flattened into a more uniform glow. It covers perhaps 90 degrees of sky, centered overhead, with no sharp structure, just the long, soft band of green, diffuse at its edges, slightly brighter at its center, breathing in its own slow way. You have watched it do everything it knows how to do tonight. You have seen the quiet arc at the horizon. You have seen the curtain rise and brighten. You have seen the substorm explode overhead. You have seen the red and the violet and the pulsating patches. You have seen the corona. You have seen the slow recovery. Now you are seeing what comes after all of that. The aurora in its resting state, still present, still active, still generating light, but no longer performing, just being what it is, in the quiet of the early morning, for no particular reason except that the sun is always streaming particles toward Earth, and the magnetic field is always guiding them to the poles, and the atmosphere is always there to receive them. There is a southern twin to everything you have witnessed tonight. At the same moment, on the opposite side of the planet, directly above the Antarctic continent, an auroral oval identical in structure to the one above you is active. The Aurora Australis, the Southern Lights, is produced by the same geomagnetic storm, the same CME, the same incoming particles. What enters the magnetosphere near the North Pole exits near the South Pole. The two auroral zones are coupled. When the northern lights brighten, the southern lights brighten simultaneously, mirror images of each other, connected by field lines that pass through the center of the Earth. The Aurora Australis is seen by far fewer people than its northern counterpart. Antarctica has no permanent civilian population. The subantarctic islands, South Georgia, Heard Island, Macquarie Island, are sparsely populated research stations. The southern tip of South America, from Tierra del Fuego and the Falkland Islands, sees the Aurora Australis at the same geomagnetic latitudes that Scandinavia and Alaska experience the Aurora Borealis. But the human infrastructure there is thin. The photographs are rare. The witnesses are few. Both ovals exist right now. Both are lit. And both, from the perspective of the magnetosphere, are the same structure seen from two different ends of the same magnetic tunnel. This symmetry extends further than the ovals themselves. The Birkeland currents that power the aurora flow in a complete circuit down through the northern ionosphere, horizontally through the ionosphere along high-latitude paths, back up through the southern ionosphere, and then outward through the magnetosphere to complete the loop. You are standing at one node in a circuit that spans the entire planet and reaches into near-Earth space. Every photon the aurora emits in the south tonight corresponds to an equivalent process occurring above you. The sky is doing the same thing in two places at once, perfectly timed, perfectly symmetrical, because the planet's magnetic field requires it. There is also an altitude dimension to the aurora that your eyes, standing on the ground, cannot directly perceive. The aurora you see is the visible portion, the wavelengths between roughly 400 and 700 nanometers that your retina can detect. But the aurora emits across a much broader electromagnetic spectrum. In the X-ray and extreme ultraviolet range, the aurora glows brightly, a glow that satellites in low Earth orbit photograph routinely, mapping the full energy budget of the auroral zones and measuring quantities that visible light alone cannot reveal. In the radio frequency range, the aurora emits strong natural radio emissions, auroral kilometric radiation that propagate outward into space and can be detected by spacecraft as far away as Jupiter. In the infrared, the upper atmosphere heated by auroral energy emission glows with a warmth invisible to the eye but measurable with thermal sensors. The aurora is far larger in energetic terms than what your eyes can see. The visible light is the narrow slice of a much broader emission across the electromagnetic spectrum. What you see is the smallest version of the thing, and it is already vast. There is a Sami word. The Sami are the indigenous people of the Scandinavian and Kola Peninsula Arctic regions who have lived alongside the aurora for longer than any written record of it exists. The word is Gwov Sahasat. It refers to the aurora, and its root is connected to the word for the light that comes before sunrise, the light that exists before the day begins, the quiet light, the patient light. Gwov Sahasat. The aurora as the light that was here before and will be here after, and is here now simply because this is where it lives. You turn slowly, taking in the full circle of the horizon one last time. North, the auroral band, its soft green persistent. South, darkness, stars, the ordinary night. East, a horizon that is indistinguishable from any other hour of the night. West, more stars, more dark, the aurora fading at its western edge. And then you walk back toward the car, slowly, unhurried. Your feet make small sounds in the snow, a compressed squeak with each step, the sound snow makes only at very low temperatures when the crystals are too cold to compress smoothly. Each step is the same, the sound is the same, the cold is the same. Behind you, the aurora continues. You are not looking at it anymore, but you are aware of it in the way you are aware of a fire when you turn your back to it. You feel it. The light is still there, the green is still there, the atoms are still emitting their photons. The sun is still streaming. The field is still carrying. The sky is still lit. You reach the car. The metal of the door handle is so cold it is indistinguishable from pain. You open the door and get inside. The interior is dark and cold and still, but it holds the ghost of warmth from the drive out, a warmth that has diminished over the hours, but has not entirely disappeared. You sit without starting the engine. Through the windshield, framed by the car's roofline, the aurora is visible, green light, moving slowly, the same light that has been moving all night. You watch it through the glass for a moment. Then you let your eyes close. The cold is everywhere now, deep in your muscles, at the edges of your awareness. But the cold is not unpleasant. It is the cold that follows something real. The cold that comes with having been outside, actually outside, in a place where the sky is not a backdrop, but an event, a participant, a presence. Your breath slows. The green light continues outside the window, though your eyes are closed to it. You know it is there. You know that somewhere above the car, above the snow, above the frozen trees, at 100 kilometers altitude, oxygen atoms are absorbing electrons from the sun and releasing green photons in every direction, downward toward you, upward toward space, sideways toward every horizon simultaneously. You know that the same process is occurring right now above Norway, above Iceland, above the Yukon, above every latitude where the auroral oval currently rests. You know that satellites are measuring it. You know that scientists in warm offices are watching readouts from magnetometers and all-sky cameras and thinking about data. You know that the sun will rise in a few hours and the aurora will become invisible, not gone, still occurring, still emitting, but washed out by the overwhelming brightness of daylight. The aurora happens in the daytime too. You just cannot see it. It is always there. The magnetic field is always bending. The solar wind is always flowing. The atmosphere is always receiving. The light is always being born and dying at 100 kilometers, 100 billion times per second, whether anyone is looking or not. You were looking tonight. That is enough. The auroral display, if you could see through your closed eyelids, and through the roof of the car, and through the first kilometer of atmosphere, is beginning another slow wave, east to west, gentle, its period about 12 seconds. It will complete this wave, and then another for the rest of the night. By the time the sun rises, the display will have moved through thousands of these cycles, each one identical to the last, each one unrepeatable in its specific detail. The magnetosphere is settling, the Berkeleyan currents are diminishing, the electrons are arriving in smaller numbers now, less energetically. The aurora is dimming slowly, degree by degree, toward its quiet background state. The night is not ending. The night has hours left. But the storm is over, and the recovery is deepening, and the sky is returning to its ordinary, extraordinary darkness. Somewhere far to the south, in cities full of light, people are sleeping. They do not know the aurora was active tonight. Their sky is orange from streetlights. They will wake tomorrow, and the night will have passed without event as far as they are aware. Here it was not without event. Here the sky was alive for 6 hours. Here the atmosphere lit up in green and red and violet. Here the solar wind arrived, and the magnetic field responded, and the atoms sang their single frequency songs until the whole sky was full of it. Here you watched. Your breathing has slowed to the rhythm of something approaching sleep. The cold outside is absolute, and the cold inside the car is becoming less so, as your body heat slowly accumulates in the small enclosed space. Your muscles release their tension one by one, the neck first, which ached from hours of looking up, then the shoulders, then the long muscles of your back. The green light outside the window continues its quiet work, particle by particle, atom by atom, photon by photon, 100 kilometers up, while you rest. If you have found something in this story, in the science, in the silence, in the particular quality of standing beneath a sky that is genuinely, verifiably, measurably alive, then a like or a subscription means more than you might think to a channel like this one. It is what keeps these stories coming. It keeps this particular kind of night alive in audio form for anyone who needs it. The aurora will be there tomorrow night, and the night after, and every clear night above the geomagnetic poles for as long as the sun burns and the magnetic field holds and the atmosphere remains. You will be there too, in some form, as long as you are here. Sleep well.